This meeting is being recorded.
For problem 6 from chapter 21, we're asked to first draw the enolate that would result with treatment of these following compounds with the strong base, sodium ethoxide. So we're asked to then draw all resonance structures of the enolate and then predict in this other part here whether or not these starting ketones, so any of these diketones or ketones here present with the enolate at equilibrium. So let's take a look at part A and what our resonance structures of the enolate ion would look like. So we see here that we have this diketone, again, in part A here, shown. And we have this alpha position here, but we also have these two down here. But we should note that this position that's in between the two ketone functional groups, that will be the spot that is deprotonated by sodium ethoxide. So that's what we see down here. We see this lone pair here. And to generate our second resonance structure, we can move that lone pair here, and that would kick one of those bonding pairs up on the oxygen. So we see that negative charge on the oxygen now, that pi bond installed in the ring. The other ketone functional group has not been changed. So we would see the second resonance structure, and then to generate our third, we would move one of these lone pairs down here to form this ketone functional group there. Then we'll move this pi electrons here over to form this bond here. And then that would generate, with this curved arrow here, movement of this bonding pair to form another lone pair on this oxygen here. So that's our third resonance structure for the compound shown in part A. And then notice that if we were to use ethoxide as the base to form the enolate, we can treat this formation of the enolate as being a complete reaction. Therefore, we could also say that the diketone would be present in very low concentrations or not at all at equilibrium. Because this resonance stabilization occurs over two oxygen atoms. So this conjugate base is pretty stable. So then we can note due to being stable, we would see only the enolate. All right, let's take a look at part B. So once again, where will we deprotonate? That's always our first question here. We have 4 alpha carbons, and if we look at this and the symmetry in this molecule, we can see that they're all going to generate the same 2 resonance structures for the enolate ion. So let's take a look at what's drawn down here. We see deprotonation at this site chosen. So to generate the second resonance structure, we would move this lone pair here to generate that pi bond, and then this bonding pair would generate a lone pair on that oxygen and that negative charge now on that oxygen. The other ketone functional group is untouched, but again, we could deprotonate any of the 4 alpha positions and generate these 2 resonance structures. We can note in this conjugate base that the negative charge is delocalized only over 1 oxygen atom now, not 2. So this deprotonation of this diketone with ethoxide would result in a mixture with both the enolate and the starting diketone at equilibrium. So we would see a mixture in this case, and not just the enolate or the diketone. So let's take a look at what's different in parts C and D. So I'm just going to deprotonate at the alpha position here. That's the only site with an alpha proton to that ketone. To generate the resonance structure, we would move those electrons there and then kick those up in the second structure. So I'm going to draw my resonance structure kind of up here, where we can see that pi bond there, and then the 3 lone pairs of the oxygen. So we have those 2 resonance structures here. And then in part D, we could choose either alpha carbon. I'm going to choose this one over here. They would generate the same resonance structures here. So let's let's move that deprotonated carbon, that lone pair there at that site onto the to form a pi bond there, and then move this lone pair up. So we're going to get this resonance structure as well. And again, we're only going to get the 2 with that negative charge on that oxygen there. And we should comment for both C and D, since we are only delocalizing that charge amongst one oxygen atom, we would see a mixture again for both C and D here of both the ketone and the enolate at equilibrium.